In our previous video, we explored LLM workflows and AI agents and saw how they differ in structure, autonomy, and use cases. In this video, we are going a step further to look at the different design patterns used for LLM workflows, the strategies and structures that make them more effective and efficient. This discussion is based on the article published by Anthropic on building effective agents. If you want to read along, we've included link to the article in the description below. A basic large language model can only work with the information it learned during training. It can answer questions or generate text, but it doesn't have access to any new information outside its training data. On the other hand, an augmented LLM is connected to tools, APIs, or external knowledge sources. This means it can go beyond what it learned during training and can actively call APIs from external sources or use new information. When we talk about agentic systems, the core is still a large language model, but it's enhanced with extra capabilities. One of the most important enhancements is RAG, or Retrieval Augmented Generation. This allows the model to retrieve up-to-date information from external sources, make connections to tools or APIs, and use memory, so that it can remember important information for future tasks. An augmented large language model can generate its own search queries when it needs more information, decide which tool or API to use to complete a task, and remember and prioritize information that might be useful later. Let's take an example of Flight Booking Assistant. Imagine you ask, "Can you find me the cheapest flight from San Francisco to Tokyo next month?" A plain LLM would struggle because it doesn't have access to real-time flight prices. It might only give you generic advice like, "Flights are usually cheaper midweek." An augmented LLM, on the other hand, can connect a flight search API, fetch live flight prices and schedules, can check or store your travel preferences for future requests, and can also compare options and highlight the suitable flight details. An augmented LLM isn't just powerful on its own, it actually serves as the building block for creating more advanced systems. And this is where LLM workflow design patterns come in. Think of it this way: the augmented LLM gives us the raw abilities, it can access tools, call APIs, pull in live information, and even use memory. But just having these abilities isn't enough. We need a way to organize and structure them so they solve real-world problems in a reliable and repeatable way. So, you can imagine it like, the augmented LLM brings the intelligence, while the workflow design patterns give us the blueprint for how to put that intelligence to work effectively. Now, let's explore some of the most common design patterns for LLM workflows and see how they're applied in practice. Prompt chaining is one of the most popular LLM workflow patterns. In simple terms, prompt chaining is about breaking down a big task into a sequence of smaller steps, where each step builds on the output of the previous one. You can think of it like a relay race. One step passes the baton to the next until the final result is reached. Here's how prompt chaining works. Each step in the process is an individual LLM call, and the output from one step becomes the input for the next. You can also add checks in between, sometimes called gates. These gates act like quality controls, making sure the process stays on track before moving forward. Workflow will exit if check failed at any step. If check passes, then it moves to the next step. After completion of all the steps, final response is returned to the user. Asking an LLM to handle everything in one go can often lead to messy or incomplete answers. By breaking the problem into smaller, manageable stages, each step becomes easier to understand, and the results are more accurate. There's a trade-off between speed and accuracy. Splitting a task into smaller steps can take a little longer, but it ensures precision and reliability at each stage and for the final outcome. When should you use this workflow? Prompt chaining works best for tasks that can be cleanly divided into fixed subtasks. Anytime a problem can be structured step by step, this approach helps the LLM deliver more dependable and accurate results. Let's see how prompt chaining works with some practical examples. Imagine you have a long research document and you want a concise summary. With prompt chaining, you break the task into smaller steps. First, divide the complete document into smaller sections. Ask the LLM to summarize each section separately. Finally, combine all the section summaries into a cohesive overall summary. By approaching it step by step, the LLM can handle the task more accurately, ensuring no important points are left out. Another example is writing a complete business plan using LLM workflow. Let's say you want the LLM to help create a full business plan. Asking for the complete plan in one go can be overwhelming and often results in an incomplete or unstructured output. Instead, we can use prompt chaining. Start by asking the LLM to analyze market trends. Next, identify customer pain points. Suggest possible solutions and strategies. Finally, combine all these insights into a well-structured business plan. Breaking the task into stages makes it easier for the LLM to handle, resulting in a more accurate and organized final plan. Routing is another popular LLM workflow patterns. Routing is a workflow where a central model, often called a router, decides which specialized agent should handle a specific task. Instead of giving one giant prompt to a single LLM and asking it to handle everything, we break the problem into smaller parts and let the router direct the traffic intelligently. This workflow allows for separation of concerns, where each agent focuses on what it does best. Each agent is given a specialized prompt. In this diagram, the user's request is received by the LLM router, which breaks the overall task into smaller, specialized steps. Based on each step, a separate request is sent to a specialized LLM, in this case, to a billing agent. Finally, the complete response is compiled and sent back to the user. Think of routing as a decision diamond. It evaluates the incoming task, classifies it, and sends it down the right path to the most appropriate agent, ensuring each task is handled by the best possible expert. When should you use routing? Routing is ideal for complex tasks where the input naturally falls into distinct categories, and classification can be handled accurately. The router itself can be an LLM or a more traditional classification model or algorithm, depending on the task. Here's a real-world example of routing, a customer support LLM workflow. If the customer asks about billing, the router sends it to the billing agent. If the request is about technical issue, it goes to the tech support agent. If it's a refund request, it's routed to the refund agent. This way, each specialized agent works with customized prompts or logic suitable to its domain, which makes the system more accurate and reliable. Let's talk about parallelization LLM workflow pattern. Parallelization is when LLMs work simultaneously on a task, and their outputs are aggregated programmatically. This helps make processing faster, more scalable, and can even improve accuracy when multiple perspectives are needed. Parallelization pattern has two different variations, sectioning and voting. In case of sectioning, a large input is divided into independent subtasks. Multiple specialized LLM calls handle each subtask in parallel. Once all the subtasks are processed, their outputs are aggregated into a final response. Parallelization can be applied to more advanced workflows like automated evaluations. Suppose you want to evaluate an LLM's performance on a prompt. Instead of having one LLM try to judge everything, you can assign different LLM calls to evaluate separate aspects of performance. For example, one LLM could check accuracy, another could check clarity, and a third could check creativity. Aggregate all the evaluations to get a comprehensive performance report. This approach ensures that each LLM focuses on a single aspect, making the evaluation more reliable and precise. As in another example, we can implement guardrails using section parallelization. Imagine a system that handles user queries but also needs to screen for inappropriate content or harmful requests. One LLM handles the core user query. Another LLM works in parallel to screen the input for inappropriate content. The results are combined to produce a safe and accurate response. This method is much more effective than having a single LLM try to handle both requirements, the core task and the guardrail checks, because it separates concerns and allows specialized processing. When to use sectioning? Sectioning works best when tasks can be independently divided, allowing LLMs to work in parallel. It's ideal for speeding up processing for complex tasks where each part requires focused attention to ensure higher quality results. Another powerful parallelization technique is voting. Voting works by running the same task multiple times across different LLM calls to get diverse outputs, and then combining these outputs in a structured way to make a final decision. This is especially useful when you want more reliable results or when a single LLM call might be uncertain. From the diagram, user request for summary of a text. This request with similar but different prompts is sent to multiple LLMs and their results are combined to get the final response. Let's go through a couple of examples for voting parallelization. Let's look at an example of reviewing code for vulnerabilities. Imagine you have a piece of code and you want to make sure it doesn't have any security issues. Instead of sending it to a single LLM and hoping for the best, you can run it through multiple LLM calls, each with a slightly different prompt or perspective. Each LLM then reviews the code and flags any potential vulnerabilities it finds. Finally, you combine all the results. If multiple LLMs flag the same issue, you can be much more confident that it's a real problem, rather than relying on just one opinion. Let's look at another example, evaluating content appropriateness. Suppose you need to check if a piece of content is inappropriate. Instead of relying on just one LLM, you can run several LLM evaluations in parallel, with each one checking a different aspect of the content like language, tone, context, semantic analysis, or safety check. Once all the evaluations are done, you can apply a voting threshold to make the final decision. For example, if 3 out of 5 LLMs flag the content as inappropriate, it gets flagged for review. The importance of this voting approach is that it reduces errors and gives you more robust outputs, because you're not relying on a single LLM to get everything right. So, when should you use voting? Voting is really useful for tasks that involve uncertainty, where getting multiple perspectives can help improve accuracy. It's also great for critical tasks, like reviewing code for vulnerabilities or moderating content, where making a mistake could be costly. And finally, voting helps you balance precision and recall. You can set vote thresholds to manage trade-offs between false positives and false negatives, making your results more reliable overall. Now, let's explore a really powerful workflow pattern called orchestrator workers. In this pattern, you have a central orchestrator, which acts like a manager, coordinating a team of worker agents to accomplish a complex task. In this diagram, user request for a summary of text. This request is sent to a central orchestrator workflow, where it dynamically breaks the request into smaller tasks based on requirement. Then each subtask is sent to its specialized LLMs, which act like a worker. Their results are taken and aggregated by the synthesizer workflow. Final response is sent to the user. What makes this workflow special is that the orchestrator dynamically breaks down tasks instead of relying on a fixed plan. It delegates subtasks to worker LLMs and then synthesizes their results into a coherent final output. This orchestrator workers workflow pattern is really useful for tasks where you cannot predict all the subtasks in advance. Let's take a software development project as an example. It all starts with a user request, which could be a task or request. In our case, it is a project development request. This request goes to the orchestrator, acting like a manager that plans, delegates, and coordinates the work. The orchestrator first plans the coding project and then assigns different subtasks to specialized worker agents. Worker 1 handles research, gathering the necessary information or requirements. Worker 2 works on back-end development. Worker 3 focuses on front-end development. Worker 4 writes and runs tests to ensure everything works correctly. Once the workers finish their tasks, their outputs are sent to a synthesizer. The synthesizer merges all the results into a cohesive final output, ensuring that the work of all agents integrates smoothly. This workflow is perfect for large, complex processes, where coordinated, multi-step efforts from specialized worker agents lead to a more efficient and accurate outcome. Let's compare parallelization and orchestrator workers to understand their key differences. In parallelization, the subtasks are usually predefined. Think of dividing a document into sections and having each section processed separately. This approach is great for speed and efficiency, but it doesn't adapt dynamically if the task changes. In contrast, orchestrator workers is all about flexibility. The orchestrator decides the subtasks dynamically based on the specific input. It coordinates specialized worker agents, integrates their outputs, and adapts as needed. So, while parallelization is ideal for tasks with a clear, fixed structure, orchestrator workers shines in large, complex processes, where coordinated, multi-step efforts from specialized agents lead to more accurate and reliable outcomes. Now let's explore the Evaluator Optimizer Loop workflow pattern designed to improve answers through checking and refining. In this workflow pattern, one LLM is responsible for generating content, while another LLM provides evaluation and feedback in a continuous loop. From the diagram, we have two LLMs, one is Generator LLM and another is Evaluator LLM. User request comes to the Generator LLM, where it generates the content based on the request. This generated content is sent to the Evaluator LLM, which evaluates the content and provides feedback. Generator LLM refine the content based on the given feedback. This process goes in loop till Evaluator LLM passes the content and final response sent to the user. This pattern is most effective when you have clear evaluation criteria and when iterative refinement adds measurable value. Two key points make this pattern very helpful. First, the LLM's responses can improve significantly when guided by feedback. Second, the LLM can generate useful feedback or evaluations on its own. Let's take writing a documentary script as an example for Evaluator-optimized loop workflow. First, the LLM generates an initial draft of the script. Next, an evaluator agent reviews the draft, checking for grammar, clarity, factual accuracy, and narrative flow. Then an optimizer agent revises the draft, improving weak points, restructuring content, and enhancing readability. The improved draft goes back to the LLM, which can refine, expand, or adjust the content further based on the feedback. This loop repeats multiple times, with the LLM, evaluator, and optimizer working together until the script meets all quality standards. As a final result, a polished, high-quality documentary script that is clear, accurate, and engaging. This whole process is very similar to how a human writer iteratively refines a document, revising drafts based on critique until it's polished and high quality. In short, this workflow is perfect for tasks where iterative refinement and evaluation significantly improve output quality. That brings us to the conclusion on LLM workflow patterns. We explored a range of powerful approaches: prompt chaining for breaking tasks into manageable steps, routing for directing tasks to specialized agents, parallelization for faster processing and robust voting, orchestrator workers for dynamically coordinating complex tasks, and the evaluator optimizer loop for iterative refinement and high-quality outputs. Each workflow pattern has its own strengths, and understanding them helps you choose the right approach for your specific project. By combining these patterns thoughtfully, you can design AI systems that are flexible, efficient, and reliable, capable of handling tasks ranging from simple document summaries to complex research, coding projects, or content moderation. So, whether you're building AI for writing, coding, research, or moderation, these workflow patterns give you a blueprint to get it right every time. And that wraps up our breakdown of LLM workflow design patterns. Let us know in the comments which design pattern you find the easiest to implement, or which one you're currently using in your own projects. If you found this helpful, don't forget to like the video, subscribe for more AI architecture insights, and hit the notification bell so you never miss an update.